Hi everyone, in this video we're going to find the shortest path, or geodesic, between 2 points on a sphere. This problem is just the extension of a previous problem where we looked at the shortest distance between 2 points on a plane. We start by drawing our axes, in this case in 3 dimensions. Then we'll draw a sphere, the center of which is the origin of the coordinate system. Let's give these some labels, x, y, and z. Now we'll draw in blue a point on the surface of the sphere. This point lies a distance r from the origin, as does any point on the surface of the sphere. And then if we want to project this point down onto the xy plane, think of it as a shadow, as if there were a light shining down from above along the negative z-axis. We have a black dot on the plane and we'll connect this to the origin. Now our blue point on the sphere lies at an angle from the z-axis, which we will call theta, sometimes referred to as the polar angle, and this projection on the xy plane, the black line, will form an angle with the x-axis which we'll call phi. Phi is commonly referred to as the azimuth angle. And it should be clear from the way I've drawn it that theta will go from 0 to pi, while phi will go from 0 to 2 pi. And let's just drop a dotted vertical line. I think it will make it clearer that this is a projection down onto the xy plane. Now the length of this line is the same as this length here. So that will be r times sine of theta. So our first step is to write down our kinematics. The first will be an expression for x. And x is equal to the projection of this line, the black line, along the x-axis. So that would just be r sine theta. And since we want to project it this way, it's cosine of phi. Similarly, the projection of this line r sine theta along the y-axis is the same as this line here, and that is equal to r sine theta times sine of phi. And then z is just the projection of the blue line in this direction. So that will just be r cosine of theta. Okay, there should be no great mystery here with what I've done. If you need to, just take a minute to satisfy yourself that what I've said is correct in light of the geometry. Let's give these some numbers, 1, 2, and 3. It should be understood from this that x, y, and z are the coordinates of any point on the surface of the sphere. The next thing to consider is, what is the incremental distance between 2 points? Well, this is just the distance formula. ds squared is equal to dx squared plus dy squared plus, because it's 3 dimensions, dz squared. That's equation 4. We need to find dx, dy, and dz, but this is easy enough because we have expressions for x, y, and z. So to find the differential of x, dx, because it's a function of 2 variables, we say that this is partial x, partial theta, d theta, plus partial x, partial phi, d phi. And similarly, we can write dy as partial y, partial theta, d theta, plus partial y, partial phi, d phi. And then, of course, z is just dead simple because it's a function of only 1 variable. What are we up to? 5 and 6. And now we can find our expression for the incremental distance. That's equal to, taking the derivative of x with respect to theta, we get r cosine theta cosine of phi, d theta. Taking the derivative with respect to phi, we get a minus sine phi. So minus r sine theta sine of phi, d phi. And then we need to square all of this. Similarly, for dy squared, we take the derivative of y with respect to theta. We get r cosine theta sine phi, d theta, plus r sine theta cosine phi, d phi. And again, we square that. Plus the z component, that's just simply minus r sine of theta, d theta, and we square it. Number 7. And so turning the page, I'll just copy equation 7 onto the new page so we can reference it. And now we've got to go ahead and square all of this. Note that every single term has an r in it, so we'll bring this out as an r squared times, and then the first 3 terms of each color have a d theta in it. So we will bring out a d theta squared. That multiplies all the first 3 terms. And then what's left in the red is cosine squared theta, cosine squared phi. The first term from the green gives us cosine squared theta sine squared phi. And then the black term, there is only one, gives us sine squared theta. Close our parentheses. Plus, now note that the middle two terms cancel. If I multiply these two together, I get the negative of these two. So those just cancel. And then finally, looking at these last two terms, they each multiply d phi, so I get a d phi squared times, from the red term, sine squared theta sine squared phi, and from the green term, sine squared theta cosine squared phi. There is no second black term for the z coordinate. Number 8. This is equal to r squared times d theta squared, and then I can take cosine squared theta out as a common factor out of each of the first two terms. So that gives me cosine squared theta times cosine squared phi plus sine squared phi, plus this guy, plus d phi squared, and then these two terms each contain a sine squared theta. I can take that out as a common factor. So sine squared theta times, and then I'm left with a sine squared phi plus cosine squared phi. Close parentheses. And close the brackets. Now, using trig identities, we know that cosine squared plus sine squared is 1. So that reduces this to 1 and this to 1. So finally, we can rewrite this as ds squared is equal to r squared times d theta squared times, and notice again we've got a cosine squared and a sine squared, so that's 1 again. So this is just d theta squared times 1 plus d phi squared times sine squared of theta. And then finally, by taking the square root of both sides, we get that ds is equal to r times the rest of it to the power of a half. These are number 9 and 10, and let's put a big yellow box around it because we're going to use this intermediate result in a minute. Now, let's consider 2 points on the sphere, P and Q. And as we've shown previously, we now need to set up an integral in order to find our functional. We can write that I, which is the distance between points P and Q, is equal to the integral from P to Q of the incremental distance ds. And that is equal to the integral from P to Q of, and then the equation from the previous page for ds, we just pop that in there, r times d theta squared plus sine squared theta d phi squared all to the power of 1/2. And this implies I can be rewritten as, let's take the r out because that's constant. So r times the integral from P to Q of, what I'm going to do with this part is I'm going to take a d theta squared out. In fact, I'm going to take it all the way out from under the square root sign. So we get d theta, since the square root of d theta squared is just d theta. And then everything inside of here, I'm just going to divide by d theta squared. I end up with 1 plus sine squared theta d phi d theta squared. And that is to the power of 1/2. Now we're able to identify our functional. Our functional f is just the integrand. It's 1 plus sine squared theta times phi prime squared all to the 1/2. Where for shorthand, I've just rewritten this as phi prime squared. Note that what we've done in dividing through by d theta is we have in effect made theta the independent variable and phi the dependent variable. Remember previously we had x and we had y was a function of x. X was the independent variable and y was the dependent variable, y and its derivatives. Well, now we have theta as the independent variable and phi, and in this case we don't have phi but just its derivative. And in general terms, I can rewrite this as f of theta and phi prime. Notice again that our functional is a function of the independent variable theta and then the derivative of the dependent variable phi. Similarly, if you consider the previous problem that we did of the shortest distance between 2 points on a plane, we found that the functional was a function of x and y prime, but not of y explicitly. And we are up to number 11, 12, 13. Now, what do we need to do? Well, we need to just take our functional and we need to substitute that into the Euler-Lagrange equation. A reminder that the Euler-Lagrange equation looks like well, now in theta phi form, looks like d by d theta of partial f partial phi prime minus partial f partial phi is equal to 0. You haven't seen it in this form yet, but if you just substitute the x with theta and the y with phi and phi prime, that would be the same form of the equation. And now since f is not explicitly a function of phi, this term becomes 0. And we can rewrite the Euler-Lagrange equation as d by d theta times partial f partial phi prime is equal to 0. We can integrate both sides and write this as partial f partial phi prime is equal to a constant, which we'll call C1. And number 14, 15, 16. And let's put a big yellow box around equation 16 because we're going to use that shortly. Okay, so what we need to do next is we need to take this expression for the functional, equation 13, and we need to substitute that into equation 16. I'll do that on the next page. Equation 13 into equation 16, and let me just copy equation 13 so we can remind ourselves of it. And now, according to equation 16, we need to take partial f partial phi prime and set it equal to a constant. Now, guys, this is just a bit of algebra. I'm going to whip through this pretty quickly, since I assume you all know how to do this, but if you need to slow it down, all the material is here for you to look at. All right, let's go. So to find the partial derivative of f with respect to phi prime, that is equal to, we're going to use the chain rule here, so that's just 1/2 times what's in the brackets to the power of minus a half, times the derivative of the inside with respect to phi prime, and that's just sine squared theta times 2 phi prime. And we can rewrite that as, notice the 2 cancels the half, sine squared theta times phi prime divided by 1 plus sine squared theta times phi prime squared, all to the power of 1/2, and that's equal to C1, our constant. Number 17. Okay, next we're going to take our denominator to the right-hand side, and we're going to square both sides. That gives us sine to the 4th theta times phi prime squared is equal to C1 squared, and then I just drop the square root sign. Take the right-hand side and distribute the C1 squared, and we get C1 squared plus C1 squared sine squared theta times phi prime squared. Now we collect all the terms with phi prime squared on the left-hand side. We take phi prime squared out as a common factor, and that gives us phi prime squared times sine to the 4th theta minus C1 squared sine squared theta. And that's equal to C1 squared. Now I'm going to solve for phi prime squared by taking this to the other side. At the same time, I'm going to take out sine squared theta as a common factor. And I'm left with C1 squared divided by sine squared theta times sine squared theta minus C1 squared. Finally, I can take the square root of both sides to give me that phi prime is equal to C1 divided by sine theta times sine squared theta minus C1 squared to the power of 1/2. That is equation 18, and we're going to put an intermediate yellow box around it. All right, you guys good with this? So the next step is now to find phi by integrating this equation. I'm going to start off by copying equation 18 to the next page. And just one thing to point out, notice that what's in the parentheses here has got to be greater than 0, or else it would be imaginary, because we're taking a square root. And since sine squared theta has a maximum value of 1, that means that C1 squared must be less than 1. So let's make a note that C1 squared is less than 1. Now, integrating both sides, we get that phi is equal to, I can take the constant outside of the integral, C1 times the integral of d theta divided by the denominator. That's equation 19. And now how do we go about integrating this? Well, we need to make a substitution. And I know I'm going to get questions from you guys. How do you find this substitution? And this goes back to integral calculus, of course. But honestly, the easiest way to do this these days is simply ask ChatGPT, and it will give you the substitution. I'm going to use that 1 over u is equal to tan theta, or said differently, u is equal to the cotangent of theta. Now, let's just draw that triangle to represent it. We've got a right triangle with an angle theta. And since we know tan theta is 1 over u, that means the opposite side is 1 and the adjacent side is u. Using Pythagoras, we can find the hypotenuse as root 1 plus u squared. Okay, so this implies that we can write sine theta as 1 divided by root 1 plus u squared. Also, we can rewrite this equation as u is equal to 1 over tangent theta, or cotangent of theta. Taking the derivative of that gives us du is equal to minus cosec squared theta d theta. Now, how do we get this? Well, 1 over tangent theta is just cosine theta divided by sine theta. Use the quotient rule and you should get this result. I can solve this for d theta by dividing both sides by minus cosec squared theta. Of course, dividing by cosec squared theta is just the same as multiplying by sine squared theta. And then finally, using the substitution above, we can find that d theta is equal to minus 1 over 1 plus u squared du. And let's number these 20, 21, 22, 23, 24, and 25. We have an expression for d theta, and we have an expression for sine of theta, and we can plug these in here. Substituting equations 21 and 25 into 19, we get that phi is equal to c1 times the integral of, and then I just simply substitute for d theta, I substitute for sine theta, I substitute for sine squared theta, and the rest is the same. That's equation 26. Now I can simplify this part. First of all, I'll take the negative outside of the integral. I get negative c1 times the integral of du divided by, what this leaves me with in the denominator is 1 plus u squared to the power of 1/2 times the rest of it. And that is equal to minus c1 times the integral of du divided by, notice in the denominator that both of these are raised to the power of 1/2, so I can bring this all together in the same parentheses. And at the same time, I'm going to distribute this across each of these. That leaves me with, if I bring this inside, 1 plus u squared divided by 1 plus u squared is just 1 minus c1 squared times 1 plus u squared. And this is all to the power of 1/2. I can simplify the denominator further. Minus c1 times the integral of du divided by, I'm going to take a c1 squared outside of here, take the square root of it, I'm just left with a c1, and then I've got to divide each of the inner terms by c1 squared. So I get 1 over c1 squared, the c1 squareds cancel, and I'm just going to distribute this negative sign. So minus 1 minus u squared, all to the power of 1/2. I know I went through that quickly, but if you guys want to slow it down, then all the steps are there. Now, if we look at this part, the 1 over c1 squared minus 1, we know that that's greater than 0 because we already said that c1 squared is less than 1. So if this is greater than 0, and we know it's a constant, we can just replace that with another constant we'll call c2 squared, a positive constant, and c2 squared will just be equal to 1 divided by c1 squared minus 1. So in the next step, we're going to replace this by c2 squared, and notice also that our c1s will cancel. Okay, so let's write that all on the next page. We've got that phi is equal to minus integral of du divided by square root of c2 squared minus u squared. That's equation 27. Now, why did I write it as a square root instead of the power of 1/2? Because this is a standard form, and you will typically find an integral in this form in any standard table of integrals. And all you need to do is look it up, or ask ChatGPT, to find that this gives us phi is equal to the arc cosine of u divided by c2 plus c3. And you might ask, why did I integrate this originally from p to q, and now I've done it as an indefinite integral? Well, I figured let's just make it generalized for any 2 points on the surface, and the only difference now is I've just added this constant of integration c3. That is equation 28. And just to remind you of equation 22, the substitution we made, that u was equal to 1 over tan theta. So we can substitute 22 into 28. At the same time, I'm going to bring this constant to the other side, and I'm going to take the cosine of both sides. So that gives me the cosine of phi minus c3 is equal to 1 divided by c2, and then using the substitution, I get a tan theta in the denominator. Now, 1 over tan theta, or cotangent of theta, I can rewrite as cosine theta over sine theta. Let's number that 29. And now using the angle difference formula, I can expand the left-hand side as cosine phi cosine C3 plus sine phi sine C3 is equal to the right-hand side. Number 30. I'm going to multiply each term by r sine theta. And let me just use a bit of color coding here. The first term becomes r sine theta cosine phi cosine C3 plus r sine theta sine phi times sine C3. And that is equal to 1 over C2 times r cosine theta. Number 31. Now, why did I use this color coding? Because if we go all the way back to the very beginning, to our kinematics, we find that what is in red, green, and black is in fact x, y, and z. So, substituting equations 1, 2, and 3 into 31, I get x cosine C3 plus y sine C3 is equal to z divided by C2. Now, one last step is let's notice that what's in blue are constants. So I can rewrite this, I take the z to the left-hand side, in the general form of ax plus by plus cz is equal to 0. Call that number 32, and we'll put a big red box around it because this is our final result. Now, what is this result telling us? Well, you should know that in 3 dimensions, this is the general equation for a plane, and it's a plane that goes through the origin because the right-hand side is 0. So, this is a plane going through the origin. Well, what does that mean? That means our solution lies on a plane that goes through the origin. Notice we've got 2 unknown constants, C3 and C2. We're given 2 points in general, point P and Q. And by applying the known x, y, and z values for points P and points Q, we get 2 equations that can be solved simultaneously for C1 and C2. If we did that, then we would end up with the equation of a plane that went through the origin as well as the 2 points in question. So what exactly does it mean that our solution is a plane through the origin? Well, let's go back for a second to what we looked at in the case of 2 points on a plane. The result we got for 2 points on a plane was a straight line, and what it meant is where that straight line intersected the plane, that was the minimum path. Turns out that when a straight line intersects a plane, you still just get a straight line. So there's nothing all that interesting in that case. On the other hand, in the case of a plane intersecting a sphere, anytime a plane intersects the surface of a sphere, the locus of intersection points will give us a circle. However, this is not just any plane. This is a plane that goes through the origin, as we said before. If you've got a plane that goes through the origin, where that intersects the sphere is not just a circle, but it's in fact something called a great circle. A great circle is a circle on a sphere whose center is the center of the sphere. Said differently, a great circle is caused when the intersecting plane splits the sphere into 2 equal hemispheres. So what does that mean? Well, if we have a plane that goes through points P, Q, and the center of the sphere, then P, Q, and the center of the sphere are all on the same plane. Any 3 points, as long as they're not collinear, will define a unique plane. So what it tells us is that if we take this plane such that P, Q, and the center point O lie on the plane, then where that plane intersects the 2 points, that will form the arc or a segment of a great circle, and that segment of the great circle represents the shortest distance between those 2 points on a sphere. So we see it here in the case of PQ. Points P and Q both lie on this plane, and where that plane intersects the surface of the sphere, that arc is the shortest distance path. On the other hand, if we're talking about 2 points that are antipodes, meaning they're polar opposites, like the North and South Pole, for example, then because those don't form a triangle, but rather those points are a straight line, there'll be an infinite number of planes that can be defined going through the 2 of them. And so if I were going from point V to point U, I could go along the great circle defined by this plane, or I could go along the great circle defined by this plane, or an infinite number of other planes in between. I should also mention that this figure of the sphere comes from Wikimedia, and it's made available under a Creative Commons license. For a link and attribute, you can find this in the video description below. Well, that brings us to the end of this video, but before we go, I just want to take it from the top again very quickly so that it can all flow. We started off by defining the kinematics related to a point on the surface of a sphere. Using those kinematics, we were able to come up with a formula for the incremental distance between 2 points on a sphere. From this incremental distance, we were able to come up with an integral for the distance between 2 points on a sphere. Based on the integral, we were able to identify our functional. We then found the correct form of the Euler-Lagrange equation based on the form of that functional. Substituting the functional into the Euler-Lagrange equation gave us an expression for phi prime. We were then able to integrate the expression for phi prime, the result of which gave us an expression for a plane that went through the center of the coordinate system, or the center of the sphere. And then we recognized the fact that this plane going through the origin, where that intersected the surface of a sphere, that formed a great circle through our 2 points in question, and the arc of that great circle between the 2 points represented the minimum length path between those 2 points. Anyway, that's all I want to say about this video. I hope you found something useful in it. If you have and you'd like to support this channel, there are a few ways you can do this. The first is by clicking those like buttons. This really helps the YouTube algorithm put this video in front of other people like you who might want to see it. Second, you can go ahead and subscribe to this channel by clicking subscribe below and then on the bell icon. This way you'll be notified of any future video releases. Remember that the notes for this video can be downloaded from the link provided in the description below. If you have any questions, comments, compliments, criticisms, I'd love to hear from you in the comments section below. Thank you for watching, and I will catch up with you in the next video.